All right, so today, plan is SMDC is here to talk to us about what we're going to do and the kind of fun, exciting stuff we're going to do for them. So I'm going to turn it over to them. This is Dr. Travis Taylor. You might have seen him on the show, at some point. But he is the technical POC, is what I call him, the TPOC from my perspective, at SMDC, who is over this project. He will be your review board chair. And then if he has other people in the review board that'll come in and see you from time to time, they can't be any worse than the teachers you had in the spring, so you should be all right from that perspective. And then some of you might know John. He's actually a student like you right now, and he's working at SMDC, and so he's going to talk to you about this as well. So with that, I'm going to turn it over to Travis and John. There you go. We'll sit back here.
So, as PJ just said, I'm Travis Taylor. I'm with the Science Technology Center at SMDC, and then my phone's got a message. But anyway, I'm in the Space Division. I'm the senior scientist there, and what our mission is to figure out how to employ and apply space technologies to give our warfighter a tactical advantage. And this isn't the big bajillion-dollar spy satellite stuff that you see in the movies. This is the, let me give you an example. If you wanted to use something like a Hubble Space Telescope, right? It takes months to get a plan through and approved and to point it wherever you want to point it and look at something. And then the data goes to a particular place on the planet. And a certain group of folks go in and look at the information and then disseminate it to the rest of the world. And that all takes a bunch of time. If you're a guy that's in Digicam, an Army soldier, and he's in an urban environment, and there's a guy shooting at him from a skyscraper two blocks or 3 blocks down, and he wants to know if he's got backup coming in the way of convoys, or if the smoke over the hill is because the building's on fire, or whatever it is, he can't get that data real time from a spy satellite, right? And you say, oh, well, we got UAVs. Turns out, UAVs are really expensive, okay? And most times, we will not send the UAVs into an area where they're going to get shot down because it's a big loss of money and a big risk. So our guys typically get stuck in a situation where they have no information to help them solve the problem that they're in and get out safely or take the objective or whatever it is they're there to do. So our goal is to come up with a way to create a tactical usage of space. And you don't realize this, or maybe you do, but the Army is who got us into space to start with. Alan Shepard's first flight into space was on a Redstone Mercury capsule Redstone rocket. The Redstone rocket was a Army missile, and it was built right here in Huntsville, right? So at any rate, our main focus right now, we have several focuses. One is we're building a new launch vehicle that will launch small satellites into space. And by small, I mean tens of kilograms, maybe 50 kilograms, and maybe 2 or 3 of those on one launch. Okay, right now, the smallest launch vehicle you can really put something to orbit with, low Earth orbit, is probably a Taurus or a Delta II, or something along those lines, and you're talking, every time you do those, it's $40 million to $70 million just for the rocket, right? Wow, that's expensive. And if you're going to fly a little doohickey that costs $150 to $1 million, you don't want to launch that on something that costs 20 times, 30 times more than that, right? So what our goal is to create a plan, number one, to get these things up there, and number two, what are we going to put up there, right? And so what we're going to talk to you today is about technologies that we need in order to make the things that we put up there useful. Our first thought, the Army has actually flown, what now, about 8 CubeSats, okay, from a 1U. How many here, are y'all familiar with CubeSats? Raise your hand if you are, so I know if you are not. Okay, well, if you're not, we're going to show you, but a CubeSat is roughly yay big. It's like 10 centimeters by 10 centimeters by 10 centimeters. If you were old enough, I'd say it's slightly larger than a Rubik's Cube, but you're not old enough to know that either. So at any rate, what most of ours are 3U in stack, which means they're about the size of a loaf of bread. So they're 1U by 3U tall. And what you put a lot of things in those. You think about this. If you have some guys in the desert in Africa or in the Middle East or somewhere, you can't see a cell phone tower for hundreds of miles, right? How do you communicate? You realize what we've been doing during since the early 90s, all the way through these engagements we've had in the Middle East over there, is we've been taking weather balloons, tying cell phone repeaters to them, and letting them go, one about every couple hours. And so that we can actually communicate with these things as they are floating away. And that's very temporary and very expensive after a while. You think about it, we've been doing it for 20 years nearly. We've lost a whole bunch of those as they crash to the desert or in the ocean or wherever they land. So what if we had a constellation of small repeaters like that in low Earth orbit that we could use to talk to? Or what if we had a small constellation of little telescopes that would give us some imaging data of stuff on the ground, right? Well, that's a whole other project for y'all to figure out, but you have to realize that the further away you are from something, the larger your telescope has to be in order for you to see it. But sometimes it might be good enough just to know if a city block is on fire or if there is a convoy moving. You know, that's a lot of useful information for folks that are getting shot at. With that said, we're going to talk about what you guys are here for. So I worked with PJ and Matt for many years, known them for a long time, and we came up with this project to support the Army's mission to create CubeSats. And one of our biggest problems in the missions that we've had is when the CubeSat is deployed from the big rocket, it comes out and we have no idea what orientation it is. We have no idea what dynamic situation it's in. Is it spinning, tumbling, falling? Is it on fire with its hair hanging? I don't know. Something's happened to it, right? And so we want to understand that. And then we want to understand how to overcome it and then put it into a decent flying orientation so that we can control it and then start using it. I was talking with PJ about this 2 or 3 weeks ago, and they went to this conference, this CubeSat conference, and it seemed like everybody there was talking about the biggest problem is tumbling. Well, so I've been doing a little bit of reading, and John and I have talked about this some. When the rocket launches, now let's give you a little example about how you get these things into space. Right now, CubeSats are tiny and they don't cost much, and so you're not going to put them on a rocket by themselves to send them into space. What you hope is somebody's got a big rocket that they're putting a big thing. It costs them $500 million into space, and there's a bunch of extra empty space on it. You can put a bunch of these CubeSats on, and when it gets up there, they pop it out. So number one, you're going to go wherever they want to go. So you're not going to the orbit you want, right? That's another reason to build a rocket, or build our own rocket to launch these things. But we don't know what happens when you get out there. So you go up, you stage a rocket. You're about to deploy its big thing. It opens up a shroud. There's pyrotechnics that goes off. So who knows what's happening to the thing up there in space? Is it spinning? Is it wobbling? Is it tumbling? Then you fire it off of a thing out of an esper rig. So if you're spinning like this, as you're going off, and you shoot your little loaf of bread satellite out of a tube, if you're spinning, what's that going to do to it? Well, as it comes out the tube, it's going to hit it, and it's going to make it spin or tumble or whatever. And so I wanted to find a way to test tumbling of these things and how to overcome them. And how do you do that in gravity and in the atmosphere? You know, you can build it on a table and do one dimension at a time, on like a air hockey table, right? Air bearing table. That's not real good. You know, it's not a real good simulation. And so I thought, well, you know, free fall is the only way to do it. You can do it on the Vomit Comet, but you only get a few seconds, 18 seconds or something with each little parabolic arc. So I don't know how much data you would get there. So I thought, well, what if we just took it way up out of the atmosphere and dropped it? And like, if you remember the Baumgartner dude that jumped the Red Bull thing where he jumped from way up there, it's about 100,000 feet where he jumped. Well, he fell for about 4 minutes, tumbling crazy before the air was enough drag to stabilize him and him act like a real parachute guy. So that's what I'm hoping that we could do. And that's what I want your mission to be, is for us to test with our very first flight test. Does it make sense to drop things from 100,000 feet or whatever? And will there be enough time there that we can get some real data as the satellites fall until they hit the appreciable atmosphere somewhere around probably 30 or 40,000 feet. So that said, my buddy John over here, I hired him over the summer to look at the tumbling problem, along with a couple other folks, undergraduate student and a graduate student, or she better be a graduate student soon. And they started working this problem in detail, doing the math and the orbital dynamics, kinematics of it. And John's going to talk a little bit about it and tell you some of the control laws and things that are required with it. And at any point, y'all have any questions, just jump in and ask, because this is kind of breathing from or drinking from a fire hydrant. And we've only got 3 or 4 months to do something, get a launch, and get a report back on it, right? So so let's jump in and let's have at it. Are there any questions so far? All right, good. John, you're going to need it. I just put on my tie, man. Put that in your pocket or wherever.
So, I'm John. I work at SMBC Technical Center, and I'm employed by Cytor Corporation. So I started out there this summer, and it's continuing on into the fall. So what I'm going to talk about is the TUMBLER project, give you a little bit of background on CubeSats. I'm glad everyone's heard of the CubeSat. And we'll talk about the control laws, like Travis said. And so most of this information is pretty generic, I think. If I get too technical, please slow me down. And if it's not technical enough, let me know. If it's all information you already know, let me know. And we can talk about more technical things. So, next slide. So the purpose of the presentation is to give you background on satellites, like I said, control systems, and the detumble problem. And I'm going to let you know some objectives for the TUMBLER project that we've designated within SMBC. So next slide. So everybody knows what a CubeSat is, right? I'll reiterate.
So they can see
That'd be a good idea. Yeah. So I'll reiterate. A CubeSat, or a nanosatellite, is a small orbital satellite. It's just like any other artificial satellite orbiting Earth, except it has mass and volume constraints in order to be considered a nanosatellite. So like Travis said, these usually piggyback on launches with larger spacecraft. So NASA, the National Reconnaissance Office, both support this. They'll launch CubeSats with their larger spacecraft. And these CubeSats are normally launched to low Earth orbit.
Let me add something from this picture. UAH has flown a couple of these, and it was really interesting. If you look at this one is PhoneSat 2.5, and you look at the antenna. It's a deployable antenna. That material right there, if you go and buy it from a place where you buy satellite parts, is going to cost you thousands of bucks. But it is the exact same materials if you go to Home Depot and you buy a tape measure, except it doesn't have the problem is, for all that money, you don't even get the inch marks on it. But it's the exact same material, and it's used the exact same way. Used to deploy it, and UAH, the way I understand, that's exactly what they did. Is they wouldn't use the tape measure on the first one anyway. So you got to be clever. But one of the things I do want to get past with where the Army is with CubeSats. Up until today, CubeSats are really a hobby kind of deal. It seems like it's kind of hobby shop or one of, everything's customized. What I would really like for us to do is start getting some processes and protocols down where we learn the standards, what we really need to do. Every time we build one of these things, we do it the same way so we know that it'll be successful when we put it into orbit. But we may want to put hundreds of these things up. You never know.
That's right. So like you said, they're attractive to the government because they're inexpensive to develop and it's a quick turnaround time. And also, you get a cheap launch. So a CubeSat is a nanosatellite that meets certain standards. So mass and volume standards mainly. And they also have some restrictions on what you can do with pyrotechnics and the electronics. And this was started in the late 1990s by Cal Poly. And it's available online. Next slide. So some applications of the nanosats. Most launched today have been tech demonstrations. So can we perform this function on a satellite that's you know, this big. So that includes like power systems, propulsion, attitude control. The military is obviously interested in them for search and rescue, reconnaissance, communications, like Travis was saying earlier. There's numerous applications of research on nanosats. And I'm going to talk about a specific example. Many of you may be familiar with the NASA Landsat spacecraft. So this is a, as Travis would say, bajillion, what word did you use? Bazillion dollar project, takes years to develop, and it's good. It gives us high-res images of the Earth, right? And it's for the benefit of the public for the most part. So there's a company, a relatively new company called Planet Labs that has done this exact same thing on a nanosatellite. Now the images are not as good of resolution, but they've done it for orders of magnitude cheaper, and it's taken less time than the Landsat project. So that kind of highlights why we're interested in nanosats. Next slide. So here's just some pretty pictures to look at. Like Travis said, they come in units of U. So that's 10 centimeters by 10 centimeters by 13.5 centimeters. Don't let that trip you up. So a 3U is just 3 of those. So the Army has launched several of them, and this is a 28 satellite flock that Planet Labs developed, and it's in orbit right now taking pictures. And as we said, UAH has developed one. If you're not aware of that, you should be. By the way, any questions at any time, please let me know. Next slide.
One thing I'd point out about the Dove Flock 1 Planet Labs, you think, oh great, we got imaging satellites, they got them in low Earth orbit, we're going to get these images back all the time because there's so many of them looking everywhere. Keep in mind, these things are small, satellites are, so they have small batteries, and they have small omnidirectional antennas. So the link budget that you can connect to them with is very small. And so y'all ever gone to a 3G area and you wanted to download a picture on your phone and it takes forever, right? Well, this is way slower than 3G in most cases because the power available and the antenna is small. So that's another piece that we've got to figure out is how do you make better power apertures, meaning more power, larger antennas. So that's something else to keep in mind.
Cool. So next slide, please. And some more pretty pictures. Several of you may be familiar with the P-pod. It's what we use to put the satellites in orbit. So all it is a box with a spring inside of it. That's all there is to it. Well, there's a little more to it than that, but fundamentally that's what it is. And so when we get to the orbit, when the launch vehicle has placed the satellite in the orbit, it just punches it out. And these come in 3Us. So it's capable of pushing a 3U CubeSat into orbit.
So I actually like to call these things the bread box because we're launching loaves of bread. That's what a 3U is. And that's a spring-loaded bread box, effectively. You open the door, it's just like a toaster, it pops it out, right? And so that, you think about it, that's the kind of scale, physical scale of these things. But now, when you go to a launch, when our last launch we did, the P-pods were stacked. I mean, it was, you know, a trunk-sized bunch of these things, and they bolt them onto the rocket, and there's a whole bunch of doors, and they'll pop open and they'll pop out once you get into your orbit deployment location. Now the problem is, we don't know what's happening when the doors spring load open. Sometimes as the CubeSats come out, maybe their solar panels get hung on the way out. Maybe the doors don't open all the way and they bang into the doors, and that makes them have some kind of dynamic response as well. So we don't really understand the deployment environment as well as what happens once it gets deployed.
So the picture on the top left is some nanosatellites being deployed from the space station. So,
and if you happen to watch the news last week, there was a Russian cosmonaut on the station working on something. He's out there and he's got, you know, the crazy cordless tools that they're doing on EVA, and he's got this CubeSat, 1U CubeSat that's tethered to him, floating behind him the whole time, and at some point he reaches over, grabs it, unclicks it, just does that, tosses it. That's how it was deployed. And that was pretty cool seeing that on the news. You think, well, you know, I hope he threw that far enough that it gets completely out of the orbit with the station, or I'm surprised NASA allowed for that, but turns out we're actually considering deploying some off the station as well for experiments. You can't do them for military purposes, but you can for experiment purposes.
Cool. Next slide. So moving on, I'll give you a little bit of background on what is called attitude determination and control on a CubeSat. So this is a subsystem of the CubeSat, and it gives the satellite the ability to point at whatever you want. So the ground, the stars, the sun, the moon. There's a lot of different applications for a control system. So for some satellites, it's just important for the mission. So if you've got an Earth imaging satellite, obviously you have to be able to point to take a picture with your camera. If you have a communication satellite, your antenna may require pointing. And for some satellites, it's crucial for them to stay alive. So if you have to point at the sun to get energy on your solar panels, you may require pointing. Propulsion events, if you don't want your satellite to re-enter the Earth, you may want to boost it back out into space. Well, that requires pointing your thruster. And there's other applications.
If you have a directional antenna for communications, and it needs to be pointed at a particular location on the Earth to within some error, then you need to be able to control the way it is pointed. So keep that in mind. You can think of a million reasons why the thing needs to be pointed in some direction, and you know where it's pointing. That's something to keep in mind. Let me give you two terminologies that you might hear. One is pointing knowledge, and one is pointing accuracy. Okay, pointing accuracy is if I can point a laser pointer at a target over there, and how well I can hold that dot on the target. That is my accuracy. It may be off by so many microradians of jitter per second, right? The little dot's wiggling around. But I know it's going to be so close to that dot within some amount of microradians per second. That is my pointing accuracy. Now, just because I have really good pointing accuracy doesn't mean I have any idea where I'm pointing, right? I need to know where I am in the universe relative to everything else very accurately to know where I'm actually pointing. So this is part of the problem, is we have to know the actual orientation of the satellite. We have to have the knowledge of where it is, where the sun is, the moon, the Earth, and some other point stars or something, to tell us exactly where it is to as good accuracy as we can. So then we can actually tell, even though we can control it accurately, we need to know what it's looking at on the ground and where that is. That's the pointing the pointing knowledge. So you need to know both of those.
So a lot of things factor into how accurately you can point and how accurately you know where you are. So like you said, mainly what affects how close you're pointing is how well do we know the attitude of the spacecraft, the orientation. So the main technical challenges in pointing are determining the attitude, like I said. So this is just what orientation is the satellite in. The control, so how accurately can we physically point it? And how do we do that? And one of the finer points that I really won't jump into in this presentation is the attitude modes in the mission planning. So this is kind of an optimization problem. If you have several targets around the Earth that you want to look at, and you have a time constraint, what is the most effective way to do that as far as scheduling? So next slide. So attitude determination, like I said, is determining our orientation with respect to either inertial space or the Earth or whatever body we're orbiting around. So we typically do this with several sensors. And the most common ones, I would say, are by measuring the magnetic field, so a magnetometer, and a sun sensor. So knowledge of each of these can give you your attitude in 3 axes to some level of accuracy.
Now, if you ever read anything about naval technology developing and how the people began to sail and circumnavigate the globe, you'll realize that not only do you need to know where the sun is relative to you, but what time it is when the sun is there. And so you also have to have a good clock on board. But good clocks are pretty easy to come by these days. I mean, my phone can hook to the international atomic clock if I need to do that. So
that's very true, and that's actually a very fundamental thing in controls is how accurately do we have the time? How accurately do we know what our location is with respect to the Earth? Not attitude, but location. So are we above Florida or Europe? That's going to depend, or the sun vector is going to depend on where you are. So there's a lot of little bitty things that factor into it. And I wanted to mention, sensors have noise, right? And they're only so accurate. So we typically filter this data before we feed it into the controller. And there's this really cool thing called a Kalman filter that you should look up if you're not familiar with. And it can predict, mathematically predict, the future attitude of the satellite. It's some really cool stuff. Kind of in-depth math, but it's worth a look.
Yeah, the best place to find it, other than just doing a Google on it, is to get an old book by Bate, Mueller, and White. It's called Astrodynamics, and it has 3 chapters on Kalman filtering, and it's the best place to start. There ought to be a class taught out of it.
Cool, so the images, this is the Earth's magnetic field. Hopefully everybody knows what that looks like. And measuring these vectors tells us information about where we are. And I wanted to mention that this is a screenshot from a software called STK. And it's pretty much the industry standard in orbital simulation and verification. So I'll talk more about that later. Next slide. So attitude control. So we talked about attitude determination. Now I'll give you some background on control. So this is physically rotating the satellite. Now that we know our orientation, how do we rotate it to get it where we want it pointed? And so this is a little bit different than turning a vehicle on the ground, because we're in a microgravity environment, right? And pretty much a vacuum. So we typically use, a satellite will typically use what's called momentum wheels or magnetorquers to actually control the satellite. And I'll go into detail on each of these. Next slide. So reaction wheels are, it's as simple as this, a wheel with a motor attached to it on the satellite. And fundamentally what this does is it trades angular momentum between the wheel and the satellite. So by spinning up the wheel, you can spin down the satellite or spin up the satellite. And it's governed by the law of conservation of angular momentum.
Y'all remember in Physics 1 when the professor brings in a bicycle wheel into class and he sets on a bar stool or a chair like this and he holds the wheel and it makes you spin in different directions and all that? That's exactly what we're doing with the satellite, right? The satellite is floating around in microgravity, so if it's holding a bicycle wheel, it's going to counter and rotate according to the bicycle wheel. So we changed bicycle wheel speeds such that to remove spins and torques from the spacecraft.
So think of it as storing energy in the wheel. It's rotating, it's moving, it has energy. So you can put that energy into the satellite or take it back out to control where it's pointing. And this is only in rotation, right? So these wheels don't actually move the satellite around, it rotates it. So advantages are it maneuvers the satellite relatively fast compared to other actuators. But disadvantages are that your wheels can only spin so fast. This is called saturation. So when they saturate, they can't put any more angular momentum into the satellite or take it out, whichever way they're spinning. And you can lose control. And what's worse is if your wheels start to slow down, it puts that angular momentum back into the satellite and can cause an extreme tumble, which sometimes you can't recover from. So
you need a way to bleed the energy off of your momentum wheel so you can slow them back down without inducing more spin onto your spacecraft. The way they did it in the 70s was they actually had yo-yos on the satellites. And if they were spinning up and the momentum wheels were saturated, they would deploy the yo-yos and they would sling out further. And it's just like, again, that Physics 1 experiment where you're spinning and the professor tells you to hold your arms out and it slows you down. That's exactly what they did. And then they would slowly bring the things back with the momentum wheels to keep them from saturating. So is that something we need to do? We don't know. We hopefully will figure out a way that we can just use momentum wheels and magnetorquers, which John's going to talk about next, and keep them from get it saturated, pull it back down, get saturated, pull it back down, and so on. And these CubeSats lives are only a couple of years anyway at best. So.
Right. So what's important to highlight here is that, and Travis talked about this a minute ago, these can be difficult to test on the ground in 3 degrees of freedom. So like you said, we can put it on an air bearing and test it in one axis, but how do you get a satellite with these momentum wheels and let it have 3 degrees of freedom and test it? It's kind of hard to do since we've got gravity in the atmosphere. So just keep that in mind. Next slide.
And keep also in mind that nothing is perfect. So we don't know that the momentum wheels are exactly perfectly only one-dimensionally planar. And so if you only have a planar table to test them on, you can't really tell if there are other modes that it's inducing onto it that you don't know about. So we really need a three-dimensional environment to test it. So you can see if spinning it this way, well, maybe it's like your wheels on your car if they ever get out of balance and it starts shaking the car, right? Well, we don't know that might not be a mode that happens in these things.
That's right. So the same applies to magnetorquers. They're very difficult to test in 3 degrees of freedom. You have the same problem where you've got gravity that restricts you from rotating the satellite in 3D. And another thing that makes them hard to test is simulating the Earth's magnetic field. So that's how a magnetorquer works, is it's a magnet, an electromagnet, that torques against the Earth's magnetic field. So when you have two magnetic field vectors, the torque is the cross product between them. So this actually kind of exposes some disadvantages to this. When your magnetorquer aligns with the Earth's magnetic field, the cross product is 0, right? So there's no torque. So that's a disadvantage in addition to being difficult to test. And with these advantages, you have unlimited momentum available, as long as your satellite doesn't run out of power. So you can continue to torque and torque and torque with the magnetorquers, whereas the reaction wheels saturate. Remember, you can only put in so much angular momentum with those. As you see in the picture, we almost always have 3 of these, one for each axis of the satellite. Next slide. So here's a very general block diagram of inputs and outputs of what are called control laws.
I just realized I won't have to dock John for correctness because those are not vectors marked on his equation.
Oh, yeah. It's implied, it's implied. So anyway, a controller is what takes an input, does some math on it, and sends commands to the actuator on the satellite. The actuator in this case being either reaction wheels or the magnetorquers. And you could have others as well. So let me just talk about the pointing controller. So it's a law that takes the current attitude of the satellite and the desired attitude, so where we want to point, does some math on it and spits out reaction wheel commands to get from here to here. So other controllers are the detumble controller, I'm going to talk about that in a second, and the momentum unloading controller. So these are all pretty typical on the satellite.
So it's a typical feedback network, kind of like a PID controller, and you've got a state. You say, okay, where am I? Where am I? What is my current status? And it says, you are here. Then it says, okay, but I want to be in this configuration. So then it does the math like the Kalman filtering. It says, okay, then you've got to make these motions to get you in that direction. And you'll make a correction, and it'll do something, and it'll look and see, okay, I'm here. Okay, I'm here. Make a correction, okay, I'm here. Just like a PID controller that you've had. You've had controls, right? You know what I'm talking about when I say PID controller?
So
yes.
it's feedback.
Yes. Raise your hand if you know what a PID controller is. Oh, wow.
So the main thing to remember is that it feeds back and iteratively corrects itself. So the satellite will look at where it is, where it wants to go, and it'll iteratively correct itself. Next slide. So let's jump into the tumble problem. This is what the project's all about, right? So when we're released from the launch vehicle, the satellite tumbles. There's no way around it. And it's a problem because we don't have a GPS lock. We don't have a sun vector acquired, so we don't know where the sun is. And we're on a race with time because our batteries are here. They've only got so much energy. And if we're going to point at the sun, we need to know the attitude of the spacecraft. But usually you can't get a GPS lock when you're tumbling.
Think about it this way. you're on the third platform at an Olympic swimming pool, and they've got a box on there that's completely dark, and you can't see out. You have no idea really where you are, but you know there's a swimming pool out there beneath you somewhere, and you have to run and jump out of this box. But unfortunately, as soon as you run and jump out of this box, there's a guy standing at the edge that's going to flip you and spin you. All right, so now you come out of the dark spinning, and you hope that you're not going to do the worst belly buster you can think of when you hit the water, right? You've got to figure out what to do in order to correct your dive so you hit the water before you hit the water. Now, the metaphor here is you've got to correct your tumbling before you run out of room, of energy on your momentum wheels, and of power in your batteries. Before they are drained down, you've got to get the thing straightened out so you can point the solar panels at the sun so they can be charging the batteries back up. Or you're never going to get into a cycle where you're controlling the spacecraft. So it's a difficult problem.
That's actually a really good way to put it. The swimming pool.
That's why I'm here.
That's actually a really good way to put it. So when you dive off, you're on a time race, right? Before you run out of power or run out of time. So it's very important to detumble is the main point of this slide. Here's another picture from STK. Next slide. So we had talked about this a little. It's a feedback type of algorithm, right? So we use the magnetorquers to torque against the Earth's magnetic field, and the sensor is the magnetometer. It measures what the magnetic field is on the satellite's body. So remember, if your satellite is spinning, the magnetic field is changing. The sensor thinks it's changing. So the change in the magnetic field corresponds to how fast the satellite's spinning. So if you feed that information back, you can torque the opposite direction and slow the satellite down. Next slide. Any questions? If this is way too technical, I can try and reiterate on some of it. Some of it, just let me know.
Or take notes and ask afterwards too, either one.
So this is probably the most technical slide in this presentation. The control law for a detumble algorithm is called a B-dot controller. And it's pretty standard on most satellites that use magnetorquers to detumble. So we're taking the time derivative of the Earth's magnetic field as measured by our sensor. So remember, if your satellite's spinning, that vector is changing with respect to your satellite. So you take the time derivative of that, and it basically gives you your spin rate. And if we put a negative torque on that cross product between the Earth's magnetic field and the magnetorquer, so remember, when you have the magnetorquer and the Earth's magnetic field, the cross product is the torque it produces. So if you counteract that, hence the negative sign, it slows the satellite down. It's essentially braking. So again, just to reiterate, the sensor is the magnetometer. So that's how you measure the B-dot term here. And the actuator is the magnetorquer.
So what are you looking for here? I mean, you guys have had calculus differential equations, right? What are you looking for? You got your magnetic dipole that you want to command. You want to point it in a certain direction. And so what do you do anytime you're controlling something? You want to speed it up or slow it down. You measure the slope, right? You measure the slope of what's happening. So you take the derivative of your magnetic field, which is changing based on you're spinning like crazy in a constant magnetic field, so which is no different than changing to your sensor. So you look at the slope in all three directions, right? This is a partial in all three directions, so that now you know, well, I'm changing really fast in X, kind of slow in Y, and not so much in Z. Oh, well, then I need to make a big correction in X, small, not so much correction in Y, and not hardly any correction in Z. And then you keep doing that, right? That's the whole point of this.
So that's actually really close to what this graph is representing. So you can see in X and Y, it was tumbling faster. So this is a simulation, by the way. It was tumbling faster, whereas Z was not. So the controller slowly drove the spin rates to 0. And bear in mind, this can take several orbits, multiple hours. So it's not a very quick controller. Magnetorquers aren't don't have a lot of torquing ability.
And that multiple hours is draining your batteries all the time because you're not necessarily pointed at the sun with your solar panels, right? Keep that in mind. The water's coming up quick and you don't want to do a belly buster, right?
Next slide. Any questions on that? I know that's kind of hard to.
If you could go back to that one, what was the constant change in Z there, that linear slope? It's because it's not really a spin, is it? It's
I mean, it would be a spin. It's
Very
just
slow
it just hasn't switched directions yet.
Okay.
So your sine, cosine. Trying to think of an example. Does that make sense?
Yeah.
It just hasn't done 360 degrees.
Yeah, so the negative lines here, so I mean zero's right in here somewhere. So it is tumbling, it's just tumbling much slower than these guys. Right? And it's more damped, where these are more like critically damped, this one is way damped, right?
And this is kind of a finer detail, but these are both, this is a matrix gain. So you see how it works on X and Y faster than Z? See how it's kind of not doing anything and all of a sudden it's effective? It's because you have a different gain on each axis. So that's really important since your moment of inertia is different on each axis. Any other questions? That was a good question. Next slide.
What is considered Z for the CubeSat, the long axis?
There's the three U axis, right?
Yeah, so typically, I have to say typically here, it's the longer side.
Okay,
So yeah, you have your 3U,
Right, so,
it's this axis.
okay. So we got X, Y, and then Z.
Correct. So that makes sense if you look at the graph. You know, your Z is different than your X and Y because it's less moment of inertia. Yeah.
Well, yeah, right, it's the skater with the arms out again, right? Because the X and Y they're like this here for the spinning.
Next slide. So there's a problem with detumble. Historically, lots and lots of nanosatellites have had trouble with this, if they've attempted it at all. So the reasons are, it all goes back to, it's difficult to test. It's difficult to validate that this is going to work before we put the spacecraft in orbit. Again, we don't have much incoming power. You're on a race with time. And you can't debug this. You essentially get one try, and if you fail, you don't really, it's hard to get a reason why did it fail. Because we can't get the satellite back, right? And a lot of times you won't have communication with it. So this is extremely difficult to debug. So here's your problem statement. How can we test and validate the algorithms and hardware for detumble of a satellite on the ground before launch, sustainably?
Or somewhere, not necessarily on the ground, somewhere cheaply.
Okay, so on the ground, let's redefine on the ground. In
Not
a
in space.
non-orbital environment. Yeah, not in space. Prior to launch.
Yes.
And we want to do it sustainably. We want to be able to do it again and again, and cost effectively. We don't want to buy a vomit comet plane that can put us in microgravity or something like that.
And that may not work anyway, because it's only 18 seconds or whatever of time to study.
What about like a chamber, anti-gravity chamber?
Yeah, how about one of those?
Well, don't they have one somewhere? Like,
Who's this ubiquitous they you're talking about?
Well, like I was trying to look it up and I thought it was like Zero G Corporation.
Yeah, zero G, that, you know, that's a whole nother lecture that I could go into. No, nobody has demonstrated anti-gravity yet, as far as I know, in any environment that I've been involved in. There are some experiments that suggest that if the experiments were analyzed properly, that there might be a loophole in physics somewhere that you could do it. But there's so much experimental error in these experiments that they all come into question. So nobody has an anti-gravity chamber yet. But you know, we can imagine it. One day we will, right?
Cold fusion too, huh?
Cold fusion is actually real. It's just not in the magnitude they said it was.
Great. So next slide. So here are some objectives that SMBC has for the TUMBLER project. Like I just said, and like Travis has said, we want to determine the effectiveness of using the high altitude balloon for testing the control algorithm, specifically DTumble. So how much time are we in free fall, and at what point does the drag overcome the ability of the satellite to turn itself?
At some point, the atmosphere will be thick enough that the falling object will become an aerodynamic object, right? With some aerodynamic coefficient. So at that point, it's no longer in test mode, it's in recovery mode.
So a question I'd like answered is how fast does the satellite, the object that we drop, naturally tumble? So that's something that's extremely hard to model unless you use like computational fluid dynamics software.
And even then, the experimental error, the
That's true.
guesses you have to make
better
are
measured.
huge. So that's a really interesting point that he says, you know, what's the natural tumble? The graph that you just saw in X, Y, and Z, right? You see that X and Y were spinning a lot, but Z wasn't. If we drop this satellite from a sideways position or a up and down position or an angular position, what's it going to do as it falls? You know, you think, well, we drop stuff all the time. You've been dropping stuff since you were a kid. You know how things fall, right? Well, remember what I said about Baumgartner earlier when he jumped off that thing at 100,000 feet in his spacesuit, and he thought he was going to be able to fall like a typical skydiver, and he tumbled for 4 or 5 minutes until he hit appreciable atmosphere, and he had no means of controlling it. So think about that. We don't really know what the kinematics and dynamics are of this situation. We can model it, but it becomes very complicated. And so if we can experimentally verify it, it'll help us make our models make sense, and it'll help us understand what's going on.
And a last objective for the project is to have data on whether we need to scale up control actuators to be able to fight the environment. So when we drop it, is the torque from the atmosphere already so great that our satellite can't turn against it? We need to know the answer to that.
We'll be a third to a fifth closer to the Earth. Is the magnetic field strong enough that if we use magnetic torquers, we need to scale for that? We will be in 1/100th of an atmosphere. Okay, that significant enough that we should account for larger momentum wheels? We don't know the answer to these questions at all. We actually have, I don't even have an educated guess what the answer to that question is. So the best way to find out things that we don't know is to experiment and read the data, right? So that's what this is all about. We're going to take data and determine if this is a way to do it. If it turns out this is a way to test satellites, we may really be on something, and you guys will be, you know, the first people involved in doing that. So this is pretty exciting to me.
Great. So just to reiterate, when I say scale up, it means make them bigger. So do we need to make the reaction wheels bigger?
Or heavier, or whatever, right?
Right.
Faster, stronger.
So next slide. And we'd like to communicate to you that there are some requirements that are going to be set, and a lot of these are obvious.
We get to set them because we're paying for it.
We would like you to deploy a parachute. So I think that actually fits in the FAA regulations. Okay.
Yeah, and we hope it works because we'd like to get the thing back to look at what happened, right?
You
Because
actually have to deploy
we're going to give you a wish list of sensors that we want to put on there, and honestly, we don't know how to get the data back other than going and getting it without spending a whole bunch of money and getting other FCC, waivers and so on.
So we need the project to comply with all the FAA regulations, and there's a list of these. And I know for a fact there's certain people in the room that are familiar with them, so look them over. They're online. We would like the payload to deploy from a sealed container, and this is just due to the fact that when we're in the launch vehicle, we're in a sealed environment.
This is that black box on top of the diving platform I'm telling you about. So we want to jump from the diving platform.
And at a bare minimum, we'd like you to fly a 9-degree of freedom IMU, which is a sensor that measures acceleration in 3 axes, gyroscope, and magnetometer. So it's 9-degree freedom because you have 3 axes of each. So at a minimum, you need to fly one of these sensors. Any questions about this? This is all pretty basic stuff. Next slide. And here's our wish list. So Travis and I and certain other people at SMDC have sat down on multiple occasions and come up with a very long list of stuff that we would like to do. So these may or may not fit within the scope of the project. And Travis may want to elevate some of these requirements.
Yeah, my number one elevation is going to be the second bullet.
Yep.
I want a GoPro camera on the deployment box and a GoPro camera on the satellite.
Oh, don't worry.
Because I want to see it as it leaves, and I want to look up as it leaves.
That wasn't
And
even an issue.
that will give us so much understanding of what's going on, to be able to go back and look at that, at the frame rate, at the high definition video.
Mhm.
I mean, we got plenty of mass budget, so I mean, it's no big deal, right? But that is the number one extra sensor, that I want on there,
Oh, don't worry.
right?
I want to
We,
see that.
we definitely want to know some other things during the drop while it's tumbling. If it's tumbling enough, are there centrifugal forces that's causing stresses and strains on the structural material? So strain gauges would be really good to have. Thermal gauges, because, in that environment, it doesn't radiate heat very well. I mean, that's all it can do is radiate. There's no air for it to cool off with. So it's all radiative, not convective cooling. And so what's happening to the material in that situation? Let's see. I would like to, if at all possible, find a way to at least get some real-time telemetry in case the chute doesn't work and it crashes and destroys itself at 130 Gs when it hits the ground. We have some data at least to go with it. Now, one possibility is that there is a waiver for amateur television. And so if you put a small, there's a band, like a ham band for amateur television, just put a small low resolution camera on it as well, we could actually get some real-time video back from it. We might have to chase it with a big antenna to keep up with it, but we can do that. So that's something else to consider. It may be too much at 100,000 feet, but it's something to consider. Let's see. I would like to command the payload drop from the ground. I've seen experiments where you use barometric pressure sensors and altitude sensors and so on, and those things always fail at some point. You might get to 20,000 feet and it'll deploy, right? So it would be much better if we can send a tone signal or whatever with FSK or whatever, and it triggers an actuator and pops the door open on the thing. Y'all can figure it out. People do this all the time. Google it. I'm sure they've done it with Arduinos, right? Let's see. Oh, and there's room, and we've got a parallel project. You're the boss of that one, right? I mean, you're the instructor of that one, right? Wait,
Yeah.
you're the instructor of that one. Okay, okay. Well, but I mean, you're teaching the class. There's two classes we're on, right? Right?
Yeah, we're all, yeah.
All right, so we have a parallel effort where we want to use the computers from modern smartphones to replace the 10 or 15-year-old computers that everybody's flying on the CubeSats. So we got room on it. We might as well stick a cell phone on it and see what it does in the environment. Use its GPS, use its camera, use IMU, use whatever's on it as part of the thing. Use it to log data if you want to. Whatever you want to do with it, fine, but I would like to start getting some information on how these things work every time we fly. Okay, and then the other one would be to measure the magnetic field at the altitudes as we're falling through it and see how it compares to orbital magnetic fields and what we need to do about scaling the magnet porters and so on. And there should be a ... right here. Anything else you can think of that's a good idea as you're building this thing, planning this flight. I'm all ears. I want it. I want the data. Right now, nobody has this data. We have no idea how to fix this tumbling problem, right? Because nobody's been able to go up and watch one do it. If we can create a way to do this and watch one do this, then that's going to be exciting, and we will have. We may improve CubeSat technology by an order of magnitude just by understanding this. So that's about all I got.
That's all I have.
Any other questions, comments? How you guys going to get there from here? Anything y'all want to tell me about what your plans are? How's this going to work anyway?
If you go to the next slide, this is my contact info.
Yeah, there.
I'm definitely okay with responding to email questions.
Yeah, feel free to contact either one of us.
Good. So my plan is actually I'm creating a spec for this test. So I want you to review it and sign off on it, and that's what we'll do. So this is kind of the good, because this was kind of the guiding stuff I needed to start the spec. of how it's gonna work.
Okay.
So I'm doing that over the next week, and I have the 3 groups that are doing this. There's a team lead, so they'll all sign off on it.
So there are 3 different teams in this class? Is that how this works?
There's one super team creating TUMBLER 1, the test, but there's a team doing the 3U CubeSat engineering test model, as I call it. There's a group working at the ejection system only, and then there's a group that's looking at the test operations and the plans that we have to put in place to do this.
Okay.
So those are the 3 teams within the team.
So the team who is building the CubeSat will be doing the
Measurement.
structure and the sensors, right?
Right, correct.
Okay.
The ejection system has to worry about the camera on the outside and all that kind of stuff. And then the test eyes have got to figure out how we're going to do all this. And then if we have to have an FAA waiver, what do we do? How do we do that? All that kind of stuff. So that's the 3 groups within this team.
Okay. And we are looking at a flight in November sometime.
Yeah, they
Because you
have by
to
December 9th.
Report
they
out
have
by
to
December
report.
the 9th, right?
Yep,
Okay.
that's the plan.
Y'all got a lot of work to do.
Yes, they do.
Y'all better get on it.
I know.
So,
That's one thing I was gonna push up, or bring up is, PJ, your schedule outlined like that we would have about a month to be building hardware. I think we're probably gonna need more than that.
Okay.
I mean,
Will
I
work.
was just wondering if there's a possibility of pushing up the PDR, CDR schedule.
we got PDR Tuesday if you want to. I don't care. You know, I mean, if y'all are, whenever y'all are ready, let's do it.
Yeah, well, we'll talk about it. I'm flexible.
And I am
just
going to
guess it.
have some SMDC, microsat, nanosat folks, including myself and John, on your review boards for each of these reviews to make sure it's going to do. So, you know, we're paying for it. We want to get something out of it, right? We want to get this data so that our missions will be successful in the future. So there are going to be some senior scientists and folks involved with the reviews. So be prepared for that.
Yeah, it's good. Any other questions?
You got us here. Ask the questions while we're here.
I'll say this will be because it's being captured on Panapto, and then Matt's got it as well. So it'll be on Angel if you want to review it and say, oh, okay, what did he say about that? You know, that kind of thing. We'll have that as well.
Is there a portal or a place where as you guys get stuff done that you will post, like you did a SolidWorks model or you did something, a place that we could go in and log on and look at the results of it?
We use Google Drive.
Google Drive through the campus, through UAH.
Can you do Google Drive at SMDZ?
I don't know if they'll let us do it. I bet they won't.
I was gonna say like Dropbox was what I do, but
You've done it from
Well,
SMBC, but down at
Dropbox
Cal.
is what's secure.
I create them.
Well, what
He's
we may
got-
have to do is do a
He's
sneaker net
Angel,
once a
he's-
week or something.
Well, he's got Angel.
Yeah, you could use
Our
Angel, the
course
course
management
management
system.
system, and you could put material up there.
Yeah.
And if
So
John
then
can
I'm gonna
access
give
it.
that task to you to pull data once a week and make me a repository somewhere on there. We'll find a place.
So we gotta figure out what we need to do about that. But yeah, because he's got Angel. 'cause
So
he's
let's
super-
make some kind of, like a class turn-in requirement that whatever you've done this week, it's in some location by whatever it is, Thursday night at midnight, I don't care.
Yeah, okay.
Or Friday at lunch, it don't matter to
Yeah.
me, but I just once a week like to be able to gauge our progress.
Okay.
Because I have people looking at me saying, what do we spend our money on?
All right. Okay.
Any other questions, comments, technical, not so technical? Logistic, programmatic? All right,
All right, cool. Thanks,
Thanks.
Travis and John, for coming out.
no problem.
And